Hey everybody, Measured Not Inferred here. I'm going to make a video today about the core concepts of mining engineering. I noticed there's a lot of videos or I don't know, resources online talking about what mining engineers do or stuff like that in very vague terms, but I'm hoping today to introduce some concepts not only to people hoping to get into the field, but also uh, anyone who wants to know if there's, for example, a mine opening up near you, or if you're in another country without a path for formal education in this sphere, you get an idea of what's going on and what's happening in your area and what are the technical challenges in opening a mine and people's perspectives from that. But it's less about perspective; it's more technical. So I've broken it down. I've broken it down to four general areas. This is going to be very high level. I might introduce some topics and not talk about them in detail, but you know what? Enough of that. I'm gonna get started. So first off is everything to do with resource classification and reporting. Ore, it might sound like a really basic term, like what is ore? Everyone has the idea of it, but it's a legally important term. You have to prove whatever you call ore. You have to prove that you can extract it at a profit, extract it and process it at a profit. You can't just say anything is ore because it has some amount of iron or gold or whatever there is in it. You have to prove that you can make money off of it. And I'll talk about how that's done later, but that's just the general concept. Also, value. Well, the value of a mineral resource. Well, what makes it up? So basically, you want to get at the metal. Oh, actually, it's not physical, but you might have like an iron sulfide. I don't know or say iron oxide. I'll say X and Y. I don't know what it is off the top of my head, but you want to get the iron, obviously. But what is in the rock isn't just pure iron; it's a mineral. So when we talk about mineral resource, we might talk about the mineral itself, and then that gets processed later on. And ore is the rock made up of the mineral. So might have iron oxide here, but you might have quartz, silicate, right next to it. And this is on a very small scale. This might be like 1 millimeter. So you can't, from a mining perspective, this is all homogeneous. It's all one thing. You don't really get up close and see it. So you're limited on what you can extract. So this whole thing is called ore if you can prove it's ore. Oh, prove it's profitable. So with that in mind, how do you quantify the metal or mineral, like, I don't want to say profitability, but I'll just get started. So grade is a measure of how much metal there is, metal not mineral, there is in any particular mass. So it's generally grams per ton. Might be generally parts per million sometimes, ounces per ton for gold. These two are for gold sometimes. Grams per ton are the most common for like copper or nickel or anything like that. And that tells you how much of the metal there is per unit of ore. And the cutoff grade is how do I explain this? So mining costs money. It's pretty obvious. And at some point you can't mine barren material and make money. At some point, you have to have a minimum amount of metal for it to be worth it. In that fulcrum where it's worth more to mine it than not mine it is a cutoff grade. It's greater than the cost of mining. Well, yeah, you can think of it like that. Once a material is worth more than it is to mine it, than it costs to mine it, then you're above the cutoff grade. Some companies, some are more strategic in how they choose the cutoff grade. For example, if you're going to make 1 cent off of a ton of material, like on paper it's worth it, but you might have better things to mine in the meantime, and you're wasting your time with that. So there's a certain amount of strategy that comes into choosing a cutoff grade with respect to time and with respect to like what you think what the price is going to be later. So that's something to keep in mind. But on a basic level, cutoff grade is like a threshold. It's a threshold amount. It's usually reported in grams per ton, or if you're in another material, it might be gold, or I mean, in gold, it might be like ounces per ton or parts per million, stuff like that, but that's basically what it is. Grade tonnage curve. Let me scroll down here. Grade tonnage curve. You're going to see this in technical reports. You know what? I'll come back to it. I'll talk about technical reports first. And then come back to it. So, as I talked about before, to prove something is ore, to say something is ore, you need to prove that's worth it, and to do that, you need to file a technical report. Ever since 1991, I want to say, BRIEX. This is like the Tacoma Narrows Bridge of mining engineering. It's pretty much every course you're going to take, or someone takes a student, they're going to talk about BRIEX. So I'm not going to talk about the details of it. Basically, a company lied about how much how much gold they had, or I don't know what they were. Yeah, they were mining gold, and defrauded. I think it was billions from investors. And the thing is, because it's really easy to lie about what's underground if no one can see it. So there's called the NI 43-101. That's the Canadian standard, but it's accepted worldwide, I believe. There might be the JORC code. JORC code is Australian. But these two, well, I'll talk more about NI 43-101 because I think it's more popular. It's more. I don't know enough about JORC to say it's not as accepted, but I know more about NI 43-101. So this is a report that you file with the regulator of your country that goes top to bottom across your everything. Mineral resource, history of the project, environment, mining, how you're going to mine it, stuff like that. Just a top-down comprehensive approach to evaluating a project. And this is how you prove that it's worth it. And this is public. Anyone can see it. In fact, if you feel up to it, I suggest that you go through and read some NI 43-101 reports, because you might be pretty cryptic and Byzantine. It's a pretty technical paper, but you're gonna see some things repeated, and those things are generally the most important. You can't go wrong by getting a feel for a project's NI 43-101, and those can be found. I know in Canada it's called CDAR.com. Just Google it. And you'll find, you gotta search. It's not a great search engine, but you'll find it eventually. Any company's NI 43-101 report, and that's the key to it. And what an NI 43-101? I'll just delete this here. Give me some room. Oh well, this is fine. Actually, give me a second here. There we go. Sorry. So what an NI 43-101? So 1 second here. So a major part of NI 43-101 is not only to describe the profitability of a project, but to disclose the resource and the reserve. Basically, the amount of profitable material or mineral resource that you have. There's different classifications for this, representing how much you know about, like how confident you are in its presence, and how confident you are in the fact that you can extract it profitably. So two big terms that you should not confuse with one another is reserve. What am I doing? And resource. Actually, I'm doing it backwards. I'm not doing it backwards, but it's more intuitive to see it like this. Resource and reserve. Because you go this way in terms of confidence. Well, there's an axis of confidence. I'm going to go this way with confidence. Oh boy, it's not good. And then this is profitability. So you start off, if you've drilled a bit and you're not really sure, there's a presence of I'm going to say a resource, but you haven't drilled it in enough detail, you call it an inferred resource. This is where the namesake of this channel comes from. An inferred resource, it's not enough. Investors don't really care about it. Usually they care about indicated and measured. Oh boy. These two, if you look at a company's any company's website, they'll talk about the M&I, measured plus indicated resource. And this is basically, well, measured is you're very confident in its presence, indicated is mediocre, but it's enough to be included. And these show that you're confident, well, you know that it's there, but you can't prove yet that it's profitable to mine. Once you do what's called a feasibility study, you get to say it's a reserve. And reserve, that's where you can say it's ore, because you showed that it's profitable. And this can be a, oh boy, what am I? A proven and probable. Probable, proven. And these are the same axis of confidence here. Generally, the path is that it goes inferred to probable, indicated. Oh, no. You know, there's not a set path. I'm just saying it because I don't really remember it. But you just need to know the general concepts here of the difference between a resource, which is not proven to be profitable, and a reserve, which is, and the difference in confidence that you have. And yeah, this is done through a feasibility study. You'll generally see young companies or young junior companies, which are the smaller side of things, or anyone who's trying to start up a new project. They talk about the pipeline just to get a project up and running. And this is the series of steps one takes to take just a property that you don't really know much about and getting to that stage where you can prove to investors that you can mine it, and then you ask for money, and then you start digging. And this generally starts with a scoping study, just to get a general feel. You might, generally a scoping study, you get some engineers there, geologists, you have some drill data. You're saying, if we were to do this, how would we do it? And is it even like on the table? Or if it's not worth it at all to even get past this point. Once you get an okay, it looks good, you do a preliminary economic assessment, I'll just say PEA, or pre-feasibility study. And this is like the midpoint. This is when you start getting a bit more serious. You start calculating things, technical properties in more detail, doing more testing, metallurgical testing and stuff like that. And once you continue, you get okay for this, it looks good, then you do a bankable feasibility study. And this is where things get serious. You start showing things like discount rate. Well, discount rate is going to be always on the table, but you're going to show things like NPV to your investors, IRR. And NPV is a net present value. Let me just distinguish these things because they're not the same. So you have this. And you'll start saying NPV, net present value, and IRR. And this IRR shows its internal rate of return. It's how much investors are going to make back on their money, or so the company says. It's very uncertain. This is why generally people ask for a high internal rate of return for mining projects. And NPV is just the net present value. It's the sum of the discounted cash flows. It's pretty much, think of it as a value of the project with the value of the project right now, how much it's worth. There's also a thing called a payback period. It's pretty much how much time it will take. Say it takes $100 million to start a project. How much time is it going to take for a person, say they give all the $100 million, for them to get it back? Just some rough numbers. IRR, I guess mining projects are getting interesting above 15%, above 20% in more risky jurisdictions. Payback period, I'm not sure, but I think it's around 2 to 4 years. It's in that scale. But that's, more than that, more than 4 years. If the project's not good, it'll generally be the same across the board. But yeah, this is just general knowledge. NPV, you might have some good projects that are small scale. If it's worth it, if it's a small project, but you get a high IRR, as an individual investor on that project, you still like it. But for companies, you want it above 100 million, I think. That's generally when projects start getting worth it to add to like a large scale, well, I would say mid-scale companies portfolio, and then large scale companies you want to get up to the high hundreds and into the billions. So that's the general idea behind resource classification and reporting. Let's see. Oh yeah, I was going to talk about a grade tonnage curve that I skipped over. So let me just delete this. Getting the feel for this. Oh, let's see. There we go. Delete that. Oh man, I'm sorry, it's taking time. All right, let's go fast. Okay, so grade tonnage curve. So material isn't binary. It's not or not. I know the feasibility study, or the NI 43-101 has to say a set number of tons or ounces. Well, it'll be tons of reserve. Well, ounces or grams of material in your reserve. But it's going to say a set number, X, that you have this much. But in reality, it's not that the case, especially when you consider cutoff grade. It's the rock is not like I said, binary. You don't have this much ore, and then all around it, it's all waste, and there's not like a clear line. It's gradual, and it's not a box. It's, it might just be think of it as like a point cloud, or might be a seam with lots of different seams that are different width and grade and stuff like that. So what you have eventually is a distribution curve. This is getting in higher detail than I wanted, but it's an important concept, and you'll see it. You'll see it everywhere. So here we go. You have a certain amount of grade, so it's grams per ton. And let's say it's copper, Cu. And this is increasing in grade. So what you have here, this is the grade curve. And this is actually, let me clarify, cutoff grade. I'm going to spend some time on this because it's sort of hard to understand, and it's a critical concept for a lot of things. So cutoff grade is a x-axis, and there's two curves on here. One is the average grade. Oh, it's starting off poorly here. I need to work on this. Something like that. Or do that better. Okay. This is the average grade of your resource, or anything above your cutoff grade. Makes sense that your average, say you have a cutoff grade of 0.1, your average is going to be, 0.1. Your average is going to be higher than that. Makes sense that the average of everything above a certain threshold is higher than the threshold. And that, yeah, that's pretty much the idea of that. And then on the other curve is tonnage. How much tonnage do you have of that material? And that decreases. It's not very smooth here. Okay, there you go. Tonnage. So, say I set my cutoff grade to 0.1. Actually, no, it's not realistic. Let me at least use a number that makes sense here. Say it's 2 grams per ton. Makes more sense. Well, I had an underground mine in mind. 2 grams per ton. Say you have an average grade of 3 grams. That means you'll have a tonnage of, what's a reasonable number for underground mine? 100 million tons. Is that reasonable? It's more of an, yeah, whatever. Let's say 100 million tons. A grade tonnage curve will show you if you increase your cutoff grade to 3 grams per ton, how much your average rate increases and how much your tonnage decreases. And you take the product of that. So say you have 100 million tons at 3 grams per ton. That'll give you 300 million grams of copper times whatever the cost of copper is. Then you get the value of what you have in the ground minus the costs and a lot of other things. But that's the upper limit. You can't make more money than what you have underground. So that gives you a basic idea of the type of resource you have. And how changing your strategy in terms of cutoff grade will change your mining strategy. Say for example, it's really hard to mine things. It costs a lot per ton to mine. It's worth it. As I said before, it's gonna increase your cutoff grade. You're gonna be able to mine fewer tons. You might have 50,000 here, but those tons are gonna be much higher in grade. It might be 15 grams per ton. Things might be more interesting here because you have to pay less money up front for infrastructure, and yeah, you'll have a smaller scale project in terms of extraction, but it might be more worth it for you to do things like this. So it just shows you that you have a resource on the ground that's inhomogeneous, that's complicated, and with a certain model, you can develop a strategy by changing cutoff grade with the different constraints you have, and figure out a strategy like that. And generally, people won't be looking at this and developing a strategy. There's different ways on. It's generally more project level view, but if you see this, it's an important concept, and it'll help you figure out the concept of mining isn't I was gonna say it isn't set in stone, but it's dynamic in terms of how you make decisions, especially in terms of the price of the material, price of fuel or operating costs and stuff like that. You can change what you're doing to respond to things that are going on. All right, I just talked enough about that. Next page. So here we have an overview of I'm going to talk about basic. I'll try to be more brief here, but everyone knows what density is, but it's probably the most important concept in mining. You have to know your materials density. It's going to be everywhere in all your calculations. How much it costs to move things, how much explosives. Well, actually, explosives is going to be not worth. You represent how much explosives you put in per ton, kilograms per ton, powder factor. Everything is a function of density. Like I said before, grams per ton. Not a function of density, but you don't do grams per meters cubed. You do everything in terms of ton. So the mass, the density of your material plays a huge role. It might not seem like it, but if you have, say you have just a seam like this, 4 tons per meters cubed, you're gonna have so much more material in terms of mass than you have like a 2 tons per meters cubed, even though you have the same volume. I know this is a basic concept, but it does go a long way. It's hard to really get your head around. You have the same bucket of material, but one might be worth 2 times more. Not just because of the grade. Because of the grade. Think about it. No, same grade per ton, grams per ton. They might have the same 4 grams per ton. But times 2 times more tonnage, you're gonna have more material. It's gonna be worth more. So even though it's the same volume and shape and everything like that, it also plays a big role in the cost of moving things. Yeah, truck here, terrible truck, but oh boy, not good. In terms of energy to get up this ramp, that's gonna be a lot more when the material's heavier. So it has a ton of implications everywhere. So probably the first thing you should ask, what's the density? That's it. Another big concept is the difference of how material, the volume it takes. Say you have, basic idea, it's just soil, just ground here, and you want to dig a hole. You're going to make this hole, say you're really motivated, you make it 1 meters cubed. You dig it out and you make a pile right here. Just for fun, or say it was a spite exercise someone made you do or whatever. You have to put your dirt back in the hole. You can fill it all the way back up and you'll still have some left over. This is because when you disturb material or you extract it, it gains in volume, it bulks up. This is because, for soil, it's in a naturally compacted state, or compacted. It has a state, and when you disturb it, the particles get further apart, and it takes energy to put them back together. You'll have to If you're really motivated, you can get a compactor or whatever, and you tap it down and really force everything back in its place. But that takes energy. And rock, I don't think you can even compact it. Once you blast rock, so you have drill hole. Once you blast it, you get it out. It's different shape, and it's not like you can compact it back into place. It's there. This is important. Well, for a lot of different reasons. I'm trying to think of an example, but say someone says, "Oh yeah, we're blasting 10,000 tons a day," or say 100,000 tons a day. Where you're gonna have, and you have whatever. I don't want to get too far into an example here. You have a bucket of X number of volume, and you say, "Oh, that fits this many tons," or whatever. But it has big implications in the sizing of your equipment, and I'll think of another example. This is I think a cool one that explains a lot of the challenges of underground mining. Say you have an opening underground. Say this is a big room, and a little bit starts to cave. You get blocks piling up. Eventually, you'll have a cave and you'll have a pile on the ground. But this volume, V1, won't equal V2. V1 will be smaller than V2. And this might keep going up until eventually the difference is made up, and then you'll have a big column that's full of crushed or broken rock. And this is because, say, there's, I don't want to get into math of it, but 1.3 bulk factor. This is the bulking factor. You have enough material that this 0.3 makes up for the initial void here. And it's all made up, and then you have a big volume of broken rock. Generally, in this case, you want a high bulk factor because you do not want this to keep going up. This is bad news. Some cases, it could keep going up if you have a material with very low bulk factor and you have a very large volume, and it might go to the surface, and then you'll have a very bad time with water coming in, and yeah, it's not going to be fun. So that's just an example of why you don't want things to get out of control, and a good example of how swell factor, some people call it bulk factor, swell factor. It's a general concept that things, when you take them out, are not the same in volume. Okay. I said I was going to make this more brief, but I'm generally going on. I'll make it fast for the rest of this section. So a big factor in rocks is how strong they are. This is very important in underground mining, but also in open pit mining because you have slopes, and you do not want those slopes to fail and fall in, because that's bad. There's a lot of different ways that people characterize rocks. Things you're going to see most common: UCS, universal, uniaxial compressive strength. This is, you have a cylinder of rock, and you put it in a press, and then boom, it breaks at a certain value, and then that's the UCS. And you do it enough times, and you have a good enough idea of what the UCS of the intact rock is. BTS is, you have a very short squat cylinder, then you force like this, and it will break this direction. And this is an indirect measure of tension. So you have UCS, which is compression. Well, actually, it's not sigma 1. Well, yeah, it's sigma 1. Actually, this is too detailed. But yeah, you have compression and you have tension. And I'll just mention briefly, shear is another important factor. What the shear strength is. This is especially important for discontinuities because you have the idea of intact rock, which is nice and strong, and there's no weaknesses in it. Well, there might be weaknesses, but there's no discontinuities and everything. It's nice and strong and cohesive. And then you have another thing called rock mass, which is, you might have a boulder which is intact, but you scale out a kilometer, or let's say a few tens of meters, and things are looking a bit more complicated. What was once nice and cohesive is now full of cracks and joints and discontinuities and things that make things very complicated. Because generally things won't break in what's nice and strong. Things will move in the direction where it's weakest. And the condition of your discontinuities, joints and faults. A joint is a discontinuity where no movement has taken place. These generally occur in parallel sets. And a fault is a discontinuity where displacement has taken place. These are generally larger and are very important in terms of how you have to design around them. They have importance in terms of seismic activity, earthquakes. The rock material around it might be sheared up and messed up and make things harder for you, so you want to stay away from faults. Joints, they're sort of everywhere. You have to deal with them. You have to know where they are, and if things are in a certain direction, you want to bolt it, or you want to develop a strategy for joints, but you can't get around them. They're everywhere. And classification systems, basically using all these parameters, it's, things might be strong in one sense, weak in another. Strong and shear, have a lot of joints. So it's hard to you say, how strong is this rock? How good is this rock? It's hard to I don't want to say it's hard. People have developed ways to just say it's X strong or it's X good. It's of course going to vary on what you're going to do with it, but there's RMR, Q, rock mass rating, Q, tunneling index, a lot of different ways that these are all empirical. I don't want, don't memorize these. These are, just know that there's things out there for taking measurements, lab measurements, and turning into just saying, how good is this rock? Is it going to fail if I try to make a tunnel into it? Well, actually, it won't even tell you that. It'll say, can I support, well, how are we going to say this? If this tunnel fails and I made the decision to tunnel into it, can I at least say that it was backed up with science? Because you get into some situations and it's super hard to know how the rock's going to behave. You just want to make sure that you did everything you could to understand how the rock works and to develop around it. Sorry, that was a bit of engineering talk. You never know what the rock is going to do. You can just try to design around it or design with that information and use the best practices that other people are doing. And RQD, I'll skip over RQD. You can, I might mention it later. It's not that important, relatively. And then stresses, basically how much stress is the rock under? Is it being squeezed? Obviously you know that further you go underground, the more weight there is above you, and the more the rock is being squeezed vertically. But a lot of people don't realize that there's also horizontal stresses. Sometimes the sideways stresses are stronger than the vertical ones, because the vertical ones, it can't be more than the density of the material times the depth, because at the surface, stress equals 0, and it equals rho gh. So that's it. That's how much it can be. Laterally, you can squeeze it as much as you want, and a lot of times it's more because, especially in Canada, you have glaciers in the past. Well, some places, anyways. Yeah, you had glaciers in the past, and things made it. Well, I'll skip over it. You had glaciers in the past. These things were equal. Glaciers are gone now. The sideways stresses have stayed the same. Vertical stresses are now 0. That's why horizontal stresses are now sometimes bigger than the vertical stresses. So you have to know that they're there. And stresses respond to how you mine. You mine a circular tunnel. Stresses that one's going through it have to go around it. It's a very abstract concept, but it is important to know stresses respond to what you're doing, and that if you have a big opening here, a tunnel that was here was once safe, now it might not be safe because more stress is going through it than once before. So that's an overview of materials and importance in mining. All right, here we get to the fun stuff. At least, it's all fun, but this is what I like. Mine design. So, say, you're given. Gotta be here. This is, say it's ore. Let's just, for the sake of things, pretend that this is ore and everything else is waste. You'll have this idea a lot because it's hard to do things more complicated than this on paper. How would one mine this? Well, you have a lot of different strategies. First thing that comes to my mind when I see this, okay, it stays thick at the top. Well, it depends on what the scale is. Say this is 100 meters. Okay, it's thick at the top, all the way through. It goes to the surface. First thing coming to mind, make an open pit. Another concept, I'll just talk about, okay, you have surface mining, which is, as I said here, you dig a big pit and you grab what's in it, and that's the mine. More complicated than that, but that's the general idea. Then you have underground mining, which, it's more varied in terms of your approaches, but you dig down, or in this case, if you have a pit, you can start from the pit. You would want to go here, boom, 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 make a ramp, or if you want to, make a shaft. Connect those, and then you can start, boom, going there. Sorry, I should stop saying boom, but this is exciting. All right, and then you start getting at the ore and start mining it out, and then you can keep going. And you go as far as you want. Well, less than 4 kilometers, let's say. That's as far as you can go for now. And underground versus surface. Now, you have a bunch of different ways you can do this. I know it's started with underground, but surface is simpler, so let's talk about that. In hard rock mining, you're pretty much only going to find open pits. This is steep slopes, and you mine progressively deeper, taking benches. Actually, I shouldn't draw them smooth. Be more realistic here. You have benches, and this is a unit of depth. And let's just say it keeps going up because you're on a hillside. Okay. You mine these progressively sideways, and that gives you enough room to mine down. Say this gets far enough back, make it abstract, then you can open up another one down here. I'll talk about mine economics a bit here. You want to go as deep as you can, as fast as you can, generally, but there's limits on how you can do that effectively, so you have to make a certain width and then go down. You can't drill down in a V, but you want to go as deep as you can, as fast as you can, because generally your material, your ore, goes at depth. Say the vein went like this. You don't want to mine waste. You want to mine ore as fast as you can. So you want to go down like this, but you can't do that. You have to have a certain angle here, or else this slope might fail. So that's the general concept. You make pushbacks that give you room. Pushback is a unit of slope extraction, or pretty much any, a bench is one unit, vertical unit of extraction. You do it in blasts. And a larger scale strategy of multiple blasts and benches is a pushback. So you make one pushback here, lets you go down a bit further, and then this might make you take another pushback, go down a bit further, and stuff like that. So that's generally how you approach pit mining. And these angles depend on how strong the rock is. If you have a lot of discontinuities running like this, that's bad news. If you have them running like this, that's better news. Generally, you're going to see an angle between 30 and 50 degrees. Just off the top of my head, it might not be true, but it's in this ballpark. 45, you can use that for a model. Let's just say 45. All right, so that's open pit. Strip mining, you only see it in coal or other soft applications. It's for coal. I'm not going to go more in detail. I'm a hard rock guy, so it's there. There's some others too. Artisanal mining. This is like what you might see in Old West movies, where you have someone in a riverbed, or you have a group of people near a riverbed or at a surface panning and then processing gold in a sluice box. It exists, especially in the developing world. It's very damaging to the environment because it's not regulated, but it's a part of, I don't say it's part of the industry because it's not part of the developed world mining industry, but there's people out there doing it, and it's very bad for the environment, but it exists. Okay. Next up, underground mining. So this is interesting because you're a bit less constrained in the third dimension. You can go up, not as easily as you can go sideways, but you're more free to go as you want. So sublevel stoping, it's the bread and butter of underground mining, I'll say. Pretty much everyone's doing it these days. But, I mean, if you can do it, you'll do it. significant downsides besides if your rock is too weak for stopes. You'll have reasons not to do it, but your default. I'll stop saying like this. It's common. You want to choose the mining method for your resource. Is just sublevel stoping is very common because you'll have underground mines. You'll have narrow veins. Well, you might have thick veins, but generally it's common to have narrow. You'll mine narrow veins because it's worth it. Surface mine, you won't mine them because it won't be worth it. Now, if you go underground, you can do it. So that's why you'll be doing it more, not because there's more of them, but because you can do it. And if they're vertical enough, sublevel stoping is, let's just have the infrastructure set up here so you have the context, shaft. And you have a ramp. Okay. When a ramp, or when any horizontal level connects to the shaft, that's called a level. So you might have a few of these. You don't want too many of them because it's expensive. Shafts are expensive. Anything around them is expensive. This is expensive to set up. So you want a few. And once, say you're someone here, you get in, you get out your level, and you get in a vehicle, and then you drive to where you need to go. So this is a level. Sublevels. A level might go to the stope, but a sublevel doesn't connect exactly to a shaft. It connects to a ramp. Actually, no. All right. Sublevel stoping. So say you have two of these levels that intersect the ore body. Between these, let me scale this up. This is the lower level. This is the upper level. Oh boy. Okay. You make these, and then this is the ore. What you do is you get a drill set up here, and you drill vertical holes. Now there's different patterns. You can do it in fans, depending on the constraints you have. But basically you drill top to bottom. You can do it bottom to top, depending on your equipment, but generally do it top to bottom. You have a thing called a raise here, because you can't blast something into nothing. If you think about it, if you have a ground here, drill a borehole, you fill it up with explosives, you set it off. You won't have, like as we mentioned before, material needs space when you break it. It's going to bulk up. If you constrain it, it's not going to break up as you want. It's just going to create cracks and the gas is going to vent out. You need to make sure that there's room for the material to expand as it breaks. Generally, surface mines, they do this because you have a blast like this, and it can go this way, and it can go this way, and there's plenty of room. Underground, you have to make room. What a raise is, in this case, or you do it a number of ways, but you make an opening, let's say like a meter wide or however big you need for that material to be able to move in, especially the first blast. So you blast this. There's enough room for it to fall in and fall into the bottom here. Then you have this pile, you take it out, and then you have enough room for the second blast if it's big enough, or you work your way in so that there's enough void for the blast you're taking. That's a bit more detailed, but sublevel stoping, you have sublevels, you drill, and then you blast. I'll select it. Now, things get very complicated when you start talking about sequences, whether you start mining at the bottom, and you work your way up, or if you work from the top, work your way bottom. In real life, it's, if you take a section this way, we're seeing it from the side here, but if you look at it from the face, say the vein is a big circle that we've been seeing from the side, you're gonna start at the bottom, and then how you're gonna do your sequence. You're gonna go up, up, cross. That's one strategy. You make a pyramid. Sometimes you want to skip one, go back to it. You have different ways of doing it so that the rock behaves the way you want it to. Because generally, having one let's say like a large aspect ratio, stresses concentrate and you have a lot of stresses running through a very small area, and then bad things happen. So yeah, and then the direction that you mine is also important, whether you want to go bottom up, generally the more preferred, or the top down if the conditions of the rock suit that better. And I don't want us to say that there's only one you can do. You can start mining from each side and work your way in. There's plenty of different ways you want to do it. Like I said, well, not like I said, but what I want to say is that you might find articles or whatever online saying there's X number of mining methods. That's not true. There's different strategies, and everyone does it a bit differently. There's names, for example, sublevel stoping, for the general strategy or the general concept. But if you want to go really into detail, you might have bottom up sublevel stoping, top down, pyramidal. You can so into detail that no two mining methods, no two mines are the same. That's why I don't like it when they say, oh, there's 4 mining methods or there's 6 mining methods. There's how many there are as the precise as you want to go. This list I made just gives a general feel for how things are done. So just keep that in mind. All right. Next up is room and pillar. This is pretty self-explanatory. This is when you have a very flat seam like this. It's obviously not really possible to drill and make stopes, so you have to access it sideways, and you make rooms and you leave pillars to support the roof. And what it looks like on a plan. So this is a section. Sorry, I should have been specifying everything is a section unless I say it's not, because I've just been drawing things. But yeah, this is a section view. So this is a surface. If you're really lucky, you can get at it from the surface here. Boom, get right in there without needing a ramp or anything. But from a plan view, what you're going to see is a bunch of pillars in a very regular fashion, P, and then the rooms. Now if you want to break it down, each unit here, there's 1 room per pillar. And you want to take as much out and leave as least in as you can safely. So, in this case, we have about a 75% extraction. And you want to maximize this as much as possible, because obviously you don't want to leave anything that's worthwhile in the ground as possible. Then you have concepts called, these are general pillars, and you have what are they called again? Panel pillars. You have, I forget what they're called exactly, but you have large pillars here that separate panels. Now this is because if this pillar fails, then these 2 pillars need to support what it was, and this might cause these to fail, and then you have the whole thing unzipping. Now if you do it without sill pillars, or I don't want to call them sill pillars, without panels, this might zip your entire mine underground. I shouldn't laugh about that. It's pretty serious. It can be very catastrophic. These panel pillars contain the stresses, contain the behavior of a failure to a specific location, and it only happened there. So that's why you want to split up room and pillars into specific panels. And then you'll have accesses here, and then you'll go in there, and then you'll work your way out. And you keep doing that. Pretty simple. You do the same. You just pretty much have to design a unit and your drifts, and then, yeah. What am I doing here? I have to pause. All right, we're back. Okay. So that's the general concept behind room and pillar mining. Yeah, ideally you want it as flat as possible, but you're never going to have that exactly, so you might have to make things at an angle, which is more difficult, but possible. Caving. Caving methods are when you let the rock fail on itself. And this is good for, well, you don't want to spend money for explosives or work when you can just let the rock break on itself and then fall to you, right? Thing is, you don't really control it. So you want this for, say, It's sort of like the compromise between surface and underground because it has the large scale. Because surface mines are huge compared to underground mines in terms of material. Caving mines are the equivalent of that sort of large scale mentality, but underground. Instead of getting this vein and only getting this and leaving the rest untouched. Say you have like a bunch of different, it's all everywhere. It's complicated. On a large scale, it's worth it, but it's just so hard to get into everywhere and mine it that you can't really use another method. What you do is you cave it. So you get underneath there, you blast it enough so that this all breaks, and as I mentioned before, you let the material cave in on itself, and then as it does that, you'll have the impact on the surface. There'll be a recessed area, but you set up all your infrastructure underneath. You might even have conveyors here to do all the, you set everything nice and nice and fancy, and you let the rock fall in on itself and do the work. Thing is, you have to take everything in one go. All of this, it better be worth it because you're gonna take it all. You can't really pick and choose where you want to go. So that's a plus and minus of, this is block caving. Sublevel caving is a bit more precise. It's more precise. I don't want to say you don't get selection because you don't get selection because with sublevel caving, it's the same concept of letting material cave on itself, but on a smaller scale. You say you have an access here. This is from a side. Everything's from the side, as I said, unless I specify. And then you go here, you blast it, and you let the material cave, and then you do the same. And as you retreat, you just keep letting the material cave as you keep retreating. And then that's how you sublevel cave. And then you do it on multiple levels. Actually, I'm not going to go into too much detail here because as you can tell, it's not really my area of expertise, but just know that the concept behind caving is you let the rock fail upon itself and you extract it from the bottom. And you can do it on a large bulk scale like in block caving, or a bit more selective and precise with sublevel caving. Some good examples. Actually, I should start using examples here so you can look up mines, but Resolution Copper. Mine. And it's not there yet. Actually, since it's not an operating mine yet, I don't think I can use it as an example, but Chiquicamata mine in Chile is a good example of what they're trying to do with block caving. I know they're going to do caving, actually. Before I say they're going to do block caving, look up Chiquicamata. It's a good example of a caving mine. Sublevel caving, Kiruna in Sweden. That's a good example. It's iron ore. It's sublevel caving. Cut and fill. This is as precise as you can get. You don't do large scale blast. You make a tunnel. You get what you can. You make another tunnel on top of that. You get what you can. You make a tunnel on top of that. You keep working your way up. Or you work your way down. This is overhand if you're going up, underhand if you're going down. You generally do it if you have a very small vein and it's, you can't really make a big stope. You have to go in. Okay, I just said stope. I realized I didn't specify it. A stope is, actually I don't even know the formal definition of it, but it's a room. I'm gonna sound stupid here. I don't know the formal definition of it, but it's basically the concept that it's the room where the ore is, or the extraction. I'm gonna say the extractive unit of ore for underground mines. So as a sublevel stoping, you access it, and then this room is a stope. Technically, ruined pillar mines, the rooms are also a stope. I think it's a stope. Cut and fill. If I apply the same definition, you could call these a stope, but generally it's for like larger scale openings. These are technically still drifts, or actually drifts is a different term. It could be crosscuts. No, I'll say drift. These are drifts. You drift into the. Oh man, I just realized I didn't even specify what a drift was. Okay. Oh, I have it right here. I was planning on talking about it. Okay, so I already talked about. All right, slope is different than stope. I was going to talk about a stope is an extracted unit or of a room underground. A slope is, you know what a slope is, but it has an important concept for surface mines. You have to properly design your slopes with benches. You have to size these benches properly so that it catches material as it falls, and that it makes sense on a terms of extractive scale. You can't make these too small, or else it's not worth it to mine. Things like that. Ramps. I'll skip that. You know what a ramp is. A shaft is, a vertical hole in the ground where there's different surfaces that go in and out. You have your cage and your skip and all that. You'll have your electrical lines or your concrete lines going through there. You'll have a bunch of your surfaces going through your shaft. It's sort of like your main artery where things go in and out of your mine. These are expensive. Cost a lot of money. If you have a shaft, you're doing good. Well, you're not doing good, but it's good. It's good to have a shaft. You also have ramps too. As I said, you already know what they are, but the important underground mines, you'll generally have the two. One for vehicle traffic, one for important movement in your main artery and stuff like that. And drifts are horizontal. Actually, I won't write this out, but they're horizontal. You might call them tunnels, but in mining you don't use the word tunnel. You have drifts, which are generally used for transport and travel. They're used for travel, and it sounds stupid when I say it, but you don't use them for any other purpose than tramming or transport or things like that. A crosscut, so you have a main drift here. Actually, this is going to be a plan view. I should specify plan. You'll have a main drift used for, it's like your highway, and then the crosscut here lets you access the stope where you mine. And you'll have a bunch of these for a vein. This is a plan view, remember. So you have your drift and your crosscuts. Crosscuts are short and they cross to get to where you want to go. And then raises are like shafts, but actually they're not even like shafts. They're just vertical openings. So imagine a tunnel, but it goes up and down. They do a lot of important things like move air and rock around. And that's the workings I was going to talking about. Other important core concepts for underground mines, well, for all mines, but actually I was going to skip blasting. Blasting, I don't want to say it's specific, but you get the idea behind blasting. It's you pretty much used everywhere. The important thing for underground mines is ventilation. For the equipment that you have and the people that you have, and it's very tailored for your mine, but you need to circulate a certain amount of air through your mine, and you do this using raises or any other way you can, but you need to circulate a lot of air, and this is going to cost millions of dollars per year in just terms of energy for powering the fans. It's a big deal for underground mines is the ventilation. You have to consider it when you design the mine. Generally, it's going to sound basic, but you want an intake, you want to go through the mine, and then you want an exhaust. You don't want to make things too complicated. So you're going to have an intake, and then you want it to get through your levels in an ideal scenario, and then you want it to exhaust here. It's not as simple as that. You're going to have a lot of, for example, a stope, make air go through like this, and it'll leave this one starved, and it's not good. So, and especially here too, it's a lot easier for the air to go short circuit there than through there. So you need to set up, different workings to control the flow of air. And it's not as simple as just setting up a simple drift across the level. You're going to have, as a plan view here, as I said, you're going to have a drift, and you have workings, and you have to make sure all of these are properly ventilated. So you might have your air going through there, but you're going to need to have a fan that will bring the air to where it needs to go. So ventilation is a huge concept. Two main strategies: exhausting. Actually, I won't even go through it, but you can blow air in, or you can suck air out, depending on what type of mine you have. One is better than the other. Yep, that's that. I think this is this section. All right, we did it. Next slide. Okay. Actually, let's just take a pause. All right, just wanted to make sure we were rolling. Realizing I'm talking longer than I thought. It's not as brief as I thought, and it's not as structured, but I think we're touching on some concepts that a lot of people haven't touched on before, and it'll be good education. So last section here is everything to do with mineral processing. I said this before, I think on the slide. I'm trying to make this brief, but I'm gonna keep my flow going and see where it takes me. So mines don't produce metal, except for gold mines. But generally, say you have an iron mine. Actually, iron's not a great example. That's okay. I know copper better. So let's say you have a copper mine. A mine doesn't produce the metal copper. The mine takes in ore, which is rock mixed in with the mineral. So you have the mineral here, which the mineral itself is made up of copper. I forget what. Let's say SO. Let's say CXSOY. It's a XY. There we go. Some copper sulfate, sulfide, whatever. Copper mixed with sulfur. It's not copper. It's another mineral. So it's there, and you have the rest, whatever, feldspar, quartz, whatever you don't want, and you turn that into concentrate. Now, what is concentrate? Concentrate is all this mineral stuff, the Cu, whatever. Actually, I'm gonna look it up now that I'm doing it. All right, I was close enough. It's chalcocite. I won't even try to spell it. It's Cu2S1, or you can have chalcopyrite, which is Cu FeS2, I believe, something like that. So might as well put a little bit of effort into these. There we go. You might have something like this: chalcocite or chalcopyrite. These are the minerals, and it's mixed in with silicates or feldspars or any other type of mineral that you don't care about. Concentrate is this pure material, this mineral in its purest form. So this patch stuff only, it's still got sulfur, it's still got some other stuff in it that you don't want, but that's bind chemically. That's not bind mechanically or physically. Physically, you can't pull the copper out of this. It is what it is, and you can't pull the copper out. You have to use a smelting process for that. Generally, smelters are located somewhere else. And what you have left is tailings. And this is the not mineral. This is the quartz. This is the silicates. This is the feldspar. This is the I don't know. I've used quartz and feldspar all the time because those are the minerals I know. I'm not a big geologist, but it's everything else. Everything else physically that you can pull out. Now this is a nice ideal case. I've shown a full 100% recovery. All the mineral ends up here and all the waste ends up there. In the real world, you're going to have a little bit of waste in here because you're not perfect, and you're going to have a little bit of mineral that you left behind. And it won't be one piece either, actually. It'll be little chunks of it embedded into the other piece. So in this one, you might have a little clump of waste here. Now, this concept will help a lot in the next step where I explain the grinding and why things are ground down. But you have to get this in mind. You have tailings, which is the waste, which are generally a slurry and deposited into tailings dams, which are big and bad and no fun for anyone. And then you have the concentrate, which you ship it off to whoever wants to pay you money for it. Generally, I'm going to say China here because I know in copper, China has a lot of smelters. Who else has copper smelters? China, Japan. I think Europe might have some. Oh, Canada has one. It's just, if you're in the business, you need to know who you can send it to. Because the thing about mining is, one concentrate is generally the same as another. You can't say, oh, I've got the best concentrate, because the best concentrate is just concentrate of whatever material you have. I mean, you can say, oh, I have less. There's some bad stuff in it. Arsenic. Arsenic's a big bad one. You might have some metals in there that you don't want. And the smelter will be like, oh no, I do not want this material, and I'm going to charge you a fee for how much you send. But if you don't have a certain level, you can't say I'm better than another type of concentrate. This is where my opinion creeps in, but why certain companies, well, any company's concentrate is about as good as anyone else's. So it's just in terms of volume. You want to pump out volume and sell as much of it as you can. You can't really work into quality, and you can't really specialize into quality as other companies do and have a competitive advantage. This is why big companies, I think, have a lot of advantage. Okay, I'm gonna stop with my opinion, but that's just good to know. And then tailings and up and tailing spawns. Talk about this later. Now this general one input, two outputs box is the basic unit of mineral processing. You have an input and you have two outputs. Yes. So this is, you generally have an input and then you refine it into good, or what you want and what you don't want, and then you can further process these. You start off, I'm talking about grinding here. Oh, there we go. Okay, so I'm going to start with grinding because this is the first part of a grinding. Yeah, first part of the mineral processing. Things are very complicated in mineral processing, and no two mines are exactly the same. I actually don't want to say that. Most mines are very different. How about that? But you're going to start off with making the big rocks and just lots of tiny, smaller rocks. And then you take those rocks, and then you're going to say, I want this there in the concentrate, and I want the bad stuff in tailings. And there's a lot of different ways you can do this, and it's very complicated and it's hard to do, but you make one. You grind and make things small, and then you separate them. And the last stage is you treat these to make it, you have concentrate, but it's wet, and you have to ship it, so you have to make it dry. So you have to dewater it. Actually, that's a bad one. There we go. Let's make a better one. Yeah, there we go. You have to dewater it, dry-ish, and then wet. It's still wet there. And then you send the dryish stuff to where you need to go. And then tailings stays wet. There's different ways you can do it. It's more accepted now to dry off your tailings. Choose some dry stack tailings if you can afford it, or you send it to a tailings pond, as I mentioned before. And this first step is critical because this decision-making process, or just the way that the process discerns the profitable stuff, the good stuff from the bad, is size dependent. How do I explain this? Okay, say you have a piece of rock here. What can you do with this piece? Well, you could say, I'm going to send it to concentrate, or I can send it to tailings. What happens if you send it to concentrate? Well, you don't really gain much. I mean, you still have the mineral, but you still have a lot of waste in it. So, yeah, it's not great either. Tailings you can send it to, but you lose out on a lot of value. So what you do? Well, actually, you wouldn't even. Yeah, I want to say this is after grinding. This is a particle. Yeah, you wouldn't just send pure rock through a process. Anyways, how you improve the process is break it down further. Or that's a bad cut here. Let's just say you broke it down like this. Actually, you can't even decide, so I'm going to do it like this. You can't pick. It breaks how it breaks. Now you get to be a bit more selective. This is a bad example because they're all sort of like half and half. Say just by chance, you break it off. Boy. There we go. Say by chance you break it off like for even further. You break it into pieces like this. Actually, I hate this example. It's very bad. All right. Say you break it. It breaks. It goes like this. Now it's pretty clear. This piece you're going to send to concentrate. This piece you want to send to concentrate. This piece you might also. Actually, this is question mark. And this you definitely want to send to waste. Even though there's a piece in there, it's mostly waste. But you're left with some imperfect thing. You have, a bit of waste here, and you have a bit of waste here. but it's better than what you had before. So this is mostly waste and a bit of ore. Now, if you grind it even more, this is getting really messy, but if you keep grinding it down, you're going to have even more selective. You're going to have a bunch of pieces, and then you can be pretty selective about where it wants to go. These were all mineral, and you send them all to mineral, and all the waste ones you can send directly to waste with very little contamination. This is why the smaller you go, the more selective you can be, and the better the quality your inputs, your outputs are going to be. Thing is, grinding costs money, and it's long. Well, I don't want to say it's long. It's expensive. So you want to do it. You want to do as least as you can to get the outcome that you want. The quantification for mineral that is lost in the process that ends up in tailings versus concentrate is called recovery. Say you sent in 100 kilograms of material, and say you're really good and 1 kilogram ended up in tailings and 99 ended up in your concentrate. You have a recovery of 99%. That's pretty good. Thing is, it's not all about recovery. Well, it is a lot about recovery, but here's some edge cases to think about. Say you have a bucket of sand, and it's all sand, but some of it is black sand, some of it is white sand, and someone asks you, "Hey, can you process it for me? I just want the black sand," and you give them one piece of the black sand, and you say, actually no, you give them the whole bucket. They say the person asks, "I want 100% recovery on this process. I want 100% recovery. Process the material, so you give me only 100% recovery. I want nothing less." What you do is just hand him the entire bucket. You didn't lose anything. You had 1 kilogram of black sand, 1 kilogram white sand. You gave him 100% what you had before. So 1 kilogram of black sand. Thing is, he won't be happy because he can't do anything with it. Nothing's been added, but you gave him 100% recovery. That's why it's important to balance the quality of your output and the recovery. Someone might say, "I want nothing but pure." So you have black sand, white sand. Say he wants nothing but the pure black sand. What you do is you pick out one piece of black sand, and you give him 1 grain of black sand, and says, "There you go. You have perfectly pure material, but this also you have 0.001% recovery." So it's that's why, like the grade tonnage curve, you have different values of performance and different constraints of your process, and these are just different ways you measure it. An ideal scenario is 100% recovery and you have 100% pure outcome. That's never the case, and you're going to have curves where you're going to have, what is this? Where's recovery in this case? Yeah, this is recovery here. You know what? I'm not entirely sure what I drew here, but you're going to have curves and it's going to be a compromise. And how much you want to compromise in either one of these curves is just a function of different parameters of your process. Okay, I think I talked in too much detail about that, actually. We'll keep going. I can skip over dewatering. Liberation, basically the word I was using that describes liberating grinding down a piece and liberating this particle so you can send it only to concentrate, and the rest you can send to tails. That's liberation. You've liberated it. And dewatering, removing the water at the end. Feed is the input. Remember the three-pronged process: tails, concentrate. Feed is what goes in. You have feed, tails, concentrate. Gang, it's also another word for tails. Actually, it's not really another word for tails. Gang, this is the mineral, and the gang is all the stuff that's not good. You want the gang to go to tails. It's not another word for tails. It's the word for the bad stuff. Call it gang. Grade versus recovery, talked about that. Concentrate, we talked about that. Okay, last concept talk about here today, or in this video, is everything to do with the environment. So, as I said before, tailings are the unfortunate byproduct of mining. It is all the gang, all the, essentially is just ground up rock with mixed with water, but it has a lot of bad implications for the environment if it leaks out. That's why you keep it into tailings impoundment. This is a cross-sectional view. You dump it in, and these are generally made out of soil from materials locally sourced on site. This could be lined with some plastic. You make sure that it's very impermeable. You just put in sensors to measure if there's any water leaking. You put in sensors here to see if the slope is stable, if you're doing a good job, and you monitor the slope all the time. And you check the water level to make sure it doesn't have the risk of overflowing. So these require a lot of monitoring, some auditing, it's an engineering project in and of itself, because you're pretty much building a dam out of material that you can find locally, ideally. You don't have the benefit of choosing your location mines. You have a mine, and you have to work within the constraints of that. So if you don't have clay to build the core, you either buy it from somewhere else or you compromise by adding some plastic liner, things like that. Inside the tailings, a dam, it's going to be mostly solids with some water, supernatant water on top. You dump it in, the solids go down to the bottom with time, and the water floats to the top. Well, it doesn't float to the top. The other particles sink and the water's left. And then what you do is you decant this. So you have a little decanting barge. You take this water out, and then you process it to eventually release it. Well, not to release it. Ideally, you want to send it back into your mill and reuse it as much as possible. But at the end of your mine, where you don't process it anymore, you have to get rid of it. Not get rid of it, but you have to process it and send it back into the environment. Yes, and tailings. They usually, just the fact that they're solids. I'm not very good in the environment, but I just know that a lot of chemicals leach out of it. Not chemicals. It can be an acidic environment if you have pyrite in your tailings. There's a lot of byproducts from the mill, but generally the bad part is acid. You could also have cyanide if it's gold mine. Cyanide is important to manage, but it generally breaks down fast in a natural environment. So yeah, that's pretty much a snapshot of what tailings are. And these are very big. They're big impoundments. You might hear, okay, this is a big concept: upstream versus downstream versus centerline. Basically, you're going to hear the word upstream as a bad no word because they're more likely to fail. And what upstream is that you have a unit of, you have a dike here, and you fill it up. Say it goes like this, and it goes off in the other direction indefinitely. And then this fills up with sand, and the water is decanted, so you have sand here. So this is tailings, but it's sand, so you can build on top of it. And you fill this one up again, and you build on top of that. The problem is, you compromise in the fact that you can't really select your building material. It is what it is, and it's sand, and water can get into it. So you have to really manage your water, because if it gets too close, poor water pressures get in, water can seep through, and it can cause failure. And this is what's bad about upstream dams. You have to really control your pond. You have to make sure you have a good distance. I think it's on the order of 200 meters. And you have to know your material, because you're building on it. Downstream tailings dam. The thing is, people do it. Why it's preferred is because, in terms of material, you don't have to. Well, actually, you'll understand it more when I draw a downstream tailings dam. A downstream tailings dam is you start off with the same unit, but rather than going towards your pond, you build away from it. And you can already see that by doing so, you have to use a lot more material, and it costs a lot more money, and it takes more space. And you can't do it indefinitely because eventually you'll run into things. You'll run out of space. But it's better, it's safer because you control everything. You select the material you want to send. You compact it as you wish. It's very well controlled. Well, I mean, you're still dumping soil and compacting it, but you can control the process much better. So that's the difference between upstream and downstream. Upstream, you can just see the material that you use is much less, and you don't run out of space. Center line is a compromise between the two. Basically, you start here and you start building up like this. It's like you do downstream on one side but upstream on the other. It's just a compromise. It looks, oh boy, it looks something like this. That's what a center line. Downstream, center, upstream. And remember, up it goes towards the water, downstream goes away from the water. So you have the tailings here, and you have the tailings here. Center line, tailings here. That's the general concept. Another relevant environmental factor is waste rock. Not all, you have material underground. Say you have ore and you have waste. You send the ore to the mill to be processed into tailings concentrate, but also you have some waste here that you even know it's not even worth it. It's not even worth it to send to the mill because there's nothing in it. So you dump it into a waste rock pile. And these are just big rock piles. Thing is, if you have pyrite or pyrrhotite, or actually I don't think pyrrhotite's that bad. I think it's mostly pyrite. Certain materials that will leach acid in a proper environment. Because if you have pyrite plus air plus water, it will leach acid. This is not good. Sulfuric acid. So what you have different strategies for this. You can contain it by making sure that you isolate and make sure that it doesn't even if acid does generate, it can't leak into the environment. So you seal it and you make sure that it's isolated. Another one is you can dump this rock underwater. There's water, but there's no air, and the reaction can't take place. So that's another way you can handle it. There's some other compromises, but you really have to make sure that you can have net acid. You can have non-acid generating. Non-acid generating. Actually, there's net and there's not. I'm forgetting. You have material that can and material that can't generate acid. You have some tests that you do for it. So I don't want you to think that all waste rock generates acid. A specific type does and needs to be properly managed through these methods. But some waste rock is just sterile. It's waste rock. You dump it. You still have to manage it because there's some things you don't want it to leak out. Sometimes just solids that you don't want to end up in the water. In general, any water on site, you have to treat it. You can't let it go out. So, yeah. And at the end of the day, at the end of the day, you can't. I've been talking for a while here. You just can't let water leak off your site. You have to manage all of it. So that's a big part of it. Last part, mine closure. People, I think there's the idea. Well, in the past, I want to say people. In the past, mines have been very poor about closing properly or ensuring their mines are properly closed. Laws in developed countries now have been developed so that this doesn't happen again. Mining now is not the same as mines in the 1950s or before, or even the 1990s and before, because the regulatory structure has changed. For example, the I-43-101 report was introduced in the early 90s, and it completely changed the game for mining. So nowadays, in developed countries, I think even mines based in developed countries operating in other countries have to post the money to close the site properly before they start working on the site. So, say you have a nice, pristine environment with some rivers, and you want to dig it all up. Okay, first of all, actually, good luck with a river here. You're not going to be able to do it. Permitting process, there's permitting involved, and you can't. It's a lot more involved than people think. So, you have to choose the sites that have a lower impact on the environment, and also before, say you want to dig in this place up, you have to post the money to close it properly before you even touch the ground. So say it's going to cost $100 million to line this whole thing up, or say it's going to be a pit. Actually, I know better underground mines. So you have to. There's a waste rock dump, and there's going to be a tailings dam or whatever. You have to give the money to the government. You don't control it anymore. Say $100 million before you even touch the land, so that in the case that you declare bankruptcy, the government can close the site for you. or use your money to close the site, even if you no longer exist. And if you do close the site, you use that money to close the site. Well, actually, you don't even use that money. You spend your own money to close the site, and as you hit certain milestones, you get the money back. So it's a pretty fail-safe way of making sure sites are properly managed, and it's pretty incredible these days of what you can do to make sites look like there's never been a mine on there. Like this, you cover it with soil, you put vegetation on there, it's gonna look like hills after a while. I'm biased because I work in mining, and people are gonna say, oh, this is not gonna be exactly the same, but it's incredible with technology today what can be done. It's not the same as before, but it can be pretty darn close, or sometimes even better in case of areas where it's already been mined before. You go in there and you have the obligation to restore the mine, the area, not to what it was before, but to something that's sustainable and actually, I'm talking for a while here because I know it's a sensitive topic, but yeah, you have an obligation to make sure that it's a safe, natural, and self-sustaining environment. So, it's a heavy topic. I know especially for those of you that have a mine opening up near you. I urge you to, read through the reports, read through the permits, and understand what's going on in that area. But if you're in a developed country, the long-term impacts might be lower than what you had in mind, less than what you had in mind. So, on that note, I hope you learned a few things today. I'm starting to lose my voice here, but it's been fun to talk about some core concepts with you guys, and hope you enjoyed it. All right, see ya.